Okay, so good afternoon, everyone. Once again, since a few more people have joined in, let us continue with whatever we were discussing on last day's class. So, if you remember, on last day's class, we had studied a specific uh, portion of amplitude modulation in the terms of sideband reduction technique. I would say in general part, or it is called as the SSB-SC. And in that, we have observed that in case of DSB-SC, okay, the fundamental advantage that we had achieved, that we were suppressing the carrier. The only problem that it still had is that it was still consuming around 2 FM or 2 W of bandwidth for the transmission. But that was subsidiarily, it was subsequently considered that if we can reduce that bandwidth as well, and if we can reduce the power efficiency, like improve the power efficiency or reduce the power loss. In order to do that, the single sideband suppressed carrier, or the one that I was talking about, that where we are suppressing the carrier as well as the sub bands, one of the sub bands for that matter, that was discussed, and this was given by the single sideband suppressed carrier. So let me just show you the previous day's class where we were. So this was the diagram and this was the consideration, and the main factor was that we were transmitting only USB or the LSB transmission. Okay, and that was the biggest advantage, because when we found out the power saving, we've obtained that for the same M, that is equal to 1, we are achieving around 83% or around 84% to be honest, with respect to SSB, whereas the same modulation index DSB is providing us with 67% of power efficiency. So that's a huge improvement that we are obtaining, and keeping the fact that we are not changing anything with the message data. Since we know that the carrier doesn't contain any message or any information, and we are already neglecting that because of DSB-SC. Now, if I finely tune the DSB-SC with some filtering action, we can actually achieve a scenario where the information is contained properly, as well as the bandwidth also reduces significantly. So that is where we found out a method of frequency discrimination method, where we found out that there is a band pass filter which will be used to tune the circuit such that only a upper sideband or a lower sideband is transmitted. All right, and keeping that in mind, we have done the overall calculation, and we have found out that although this method is pretty good and theoretically it is very much possible to obtain a result of this nature, the practical problem that comes in is that the highest frequency of the LSB, this point, keep it this is very important. So please remember this carefully. Okay. So if you consider the highest post point for the LSB, okay, 1 minute. Yeah, so the highest most point for the LSB is almost equivalent to the lowest most point of the USB. That means that both of these two factors, okay, A and B point I mentioned, they are very close to each other. So if this is the case, okay, then the problem that we have is that we will always require a very high cutoff filter. Okay, and the high cutoff filter in that way, from the design aspect, that we will need a crystal resonator with having a very high Q factor, which is a very impractical, or I won't say it's not possible, but it is basically it's a wastage of money for that matter. You can say, like, it won't be a cost effective solution at all. So that is where the phase shifting method came in. So the problem with frequency discrimination method was addressed properly with the filtering action, but the major concern is the filter design. It's not about the transmission or the simplicity of the thing, because if the filter is not matching in case of SSB particularly, there is always a chance that the portion of the LSB will mix up with the USB, and hence there will be problem at times. Okay, so this is only for SSB I'm talking about. So that, keeping that in mind, phase shifting method, this was also introduced. As I showed you the diagram also, it was very similar, that we had a minus 180 degree phase shift that was introduced in case of the phase shifting method. Why I didn't show it? Because it's mostly a balanced modulator that we had done in DSB-SC. So the diagram was already there in the previous case, I think. Sorry, I think somewhere over here. Yeah, this was the phase shift method. Okay, so already we had discussed this in some time back, and so regarding that regarding that also we have observed that same as that of balanced modulator, we will also have a kind of frequency and phase error associated with this kind of a detection, and that's why it is not very I would say convenient to actually use SSP for the broadcasting purpose, because the frequency stability is so dicey and it's so vulnerable because of the filtering action and all. It is not preferred at all, although it is supposed to give us the best solution. Understand? So that is the main purpose. And also, if I go on doing the detection, there also the coherent detection, already we had discussed this principle in DSB-SC as well, where there will be a local oscillator frequency which will be exactly tuned to the carrier signal. And based on the product modulator and a low pass filter, we will generate the modulating signal. So all the calculation I did over here, and we have observed that the unwanted terms can be filtered out using the filter, and the remaining term which you're looking at 1/4 of ECXT, this is the one that we are looking at as the final outcome. Okay, so that is XT is basically the modulating signal. So we are receiving back the transmitted signal XT from that particular circuit. And also here you can observe that if the as we all know that for the same purpose in DSB-SC also we discussed the same thing, that when we are doing a coherent detection, always there is a problem that the phase shift will be there, and that's why the phi came in as our as for our discussion, that the phi is the phase difference between the tuned the local carrier and the transmitted carrier. So that again came up to an idea that there will be a non-uniformity that will be taking place while we are taking into account this particular method. So now today so this was a basic wrap up to what we had discussed on last day's class. So keeping this in mind, what we have observed that SSB ideally should be the main objective. Okay, if I happens to say from the clarity of the transmission is concerned, or with respect to the what I will say, if you consider the nature of a modulation is concerned, so it's a very nice process. But since it requires that sharp filtering, okay, it is not very common in transmission case. So keeping this in mind, scientists, engineers, they found out a new method. Okay, so that will have the drawbacks taken care of. Okay, and it will be somewhere in between DSB and SSB. So what I mean is that the technique that we are going to discuss, so DSB-SC is somewhere over here, okay, and SSB-SC is somewhere over here. So in between there is something in middle, and that is called as the vestigial sideband carrier. So this is called as vestigial vestigial sideband transmission. Now this is, as I mentioned over here, it is the somewhere in between the two transmission scheme. So that definitely means that VSB will definitely have no carrier. That is for sure, because it is more than DSB-SC. And the thing is, it will also have power efficiency, which is pretty much high. The only and the most problematic scenario of SSB was the filtering action. If you just now we had discussed that we will have issues with the high cutoff filter. So in order to avoid that, what in vestigial sideband we usually mention is that here desired, I'll write it here, please make a note of it, that because this is the fundamental of VSB. So desired sideband, that is ideally suppose it's an upper sideband, suppose, or a lower sideband, suppose, as mentioned in SSB also. So desired sidebands are allowed, okay, to pass completely, So this is same as that of SSB, but along with that, okay, plus just a small portion, okay, and this portion is ideally called as the vestige. Okay, from that only the term came in. Just a small portion of the undesired signal, undesired sideband, okay, are also, or rather is also allowed. So what does that mean? That if you are transmitting the USBs, okay, if you are transmitting the USB, along with the USB, a portion of the LSB will also be included. So hopefully I have the diagram with me. No, I don't have the diagram here. Let me you just give me 1 minute. I'll just show you the diagram in 1 minute. Okay, I'll just stop sharing. 1 minute, you give me, because otherwise I have to draw once again, which will take some time. Let me just show you the diagram for you. Okay. Put it over here. Yeah. All right. So let me start sharing once again. All right. So if you observe, this is the diagram that I'm talking about. So you can clearly see that. Let me make it full screen. So this is ideally the diagram I was talking about. So you can see, observe very clearly, the diagram is anyway self-explanatory. You can see this is the full USB. So this is the wanted or the desired sideband. Okay, suppose. And this portion, the shaded portion that you're looking at, this is part of LSB, which is undesired as far as the SSB is concerned. But what happens in this process is that you can see that very clearly that definitely there is an increase in the band. Why? Because you can check here the final value, final frequency over here is FC plus FM. Suppose I took this, okay? And the last portion over here, okay, this small little segment that you are talking about, this is called as FV. Now FV stands for the vestigial band. Okay, so FC plus FM, okay, and you can see this is the center frequency FC and this is FV, this whole thing. So FC plus FM minus FC, so this is the one of the band. Okay, this is this portion, this I'll put it some kind of a other stripe, so red color stripe. So this is this particular bandwidth, okay, FC plus FM minus FC minus F of V. So this will be the total bandwidth. Just check it once again. I'm doing it. So this portion, okay, plus this portion that I'm talking about. So FV is the vestigial band, So the portion of the LSB that has been added up with the USB. And the portion that you are talking about here, that has a bandwidth FC plus FM minus FC. So this gets cancelled. So you are having FM minus FB. FM minus. It should be plus, I think. Yeah, it should be plus, I think, because FC plus FM, the last point over here will be FC. Okay, I'll do it once again. See, this point here is FC and this is FV. Okay, so the total bandwidth, if you're looking at, that will be nothing but FM plus FV. Okay, so it is ideally FC plus FM, okay, minus FC plus FV. So this will be the structure of it. So you can see over here that since FC will get cancelled out, so then we are getting this FM plus, this should be plus actually. Okay, so this is the band that we are talking about. So you can observe that which was 2 FM in case of normal AM, or even in case of DSB SC, okay, it was 2 FM, something like this. Although in SSB it was coming as FM. Okay, here we are getting a different value altogether, and this when calculated is estimated that it is around 25% more than SSB bandwidth. So definitely there is not the bandwidth efficiency, if you call it, it is not the same as SSB. But the greatest advantage of VSB is that here the unwanted, or rather I would write here that high cutoff, because this is a tremendously advancement. This is a huge improvement to SSB, that high cutoff filters are not required. So this is the fundamental advantage of VSB. Because here, as you are allowing a small portion of the LSB to be getting transmitted, so you don't need a very high cutoff filter to neglect that portion. All right, so that is why some portion of LSB, if it comes, we don't need to worry much because the VSB allows that to happen. So that's why SSB, it is less than the efficiency of an SSB, but it is superiorly greater than the DSPSC. So that's why if I go back to our writing where it was somewhere here, yeah, so it was, you can see, observed here that VSB lies somewhere between SSB and DSPSC. All right, so this is one of the advantage of VSB and the vestigial sideband and how it is used for it. Naturally, the generation of this will also be very simple in a way that we can have a SSB signal generated or maybe a DSB signal generated, and we can have a filter, okay, which can be tuned in such a manner that it will allow a portion of the USB and a portion of the LSB. So if I go to the generation of a signal, so suppose the representation would be like this, something like this. ST, okay, this is the final outcome I'm talking about. This should be something like VT convolution. This is called as convolution operator multiplied by HT. This is in time domain representation. Don't get confused. This VT is nothing but the DSB signal. Okay. So this is the DSB signal, just like we were doing it for the SSB, the same way we are trying to do. So VT is there and there is a convolution, that operation is going on, and that is convoluted by HT, where this HT is representing the impulse response. Again, something which you might not be knowing it. So impulse response of the sideband. Okay, so it means basically it represents, this HT actually represents that the frequency domain representation or all the frequency bands which are present in the sidebands. Because you can observe that in case of VSB, we are allowing a portion of the unwanted band also to be transmitted together. So if I convert this into frequency domain, if I frequency transform, then S of F, okay, the frequency domain representation, again Fourier transform is what we are doing. This will be represented HF multiplied by HF. This is the advantage, one of the advantage of, in fact, Fourier transform, that a convolution operation, this convolution, no, this is out of the context as of now, but this convolution actually is basically a multiplication of complex numbers, complex like I would say numbers in this case. So complex multiplications. Now using this transformation, if I go to a frequency domain, this becomes a trivial multiplication, normal multiplication. So we can analyze it like a product modulator, just like that. And further, we can write this as VC by 2 x of F minus FC plus x of F minus F plus FC. This comes in from the principle of Fourier transform itself. So I'm not going much there. So this is VF. VF is represented by this, and this is multiplied by some kind of an HF over here. All right, so this is how we actually will generate it, and this portion that you're talking about, the whole thing that we are looking at over here, this is nothing but the VSB signal which is generated. Got it? So this is how we are actually generating it, and naturally you can see that mostly it will depend on the DSB signal as well as the sideband that we are going to allow, how much we are going to allow to happen. Okay, so a portion of the sidebands of the unwanted signal, anyway the wanted signal will be there, but the unwanted FB, how much we should keep as FB, that is dependent on the designing criteria. All right, so this is about the process that is involved with the generation, and as far as the detection is concerned, since we are discussing the transmission as well as the reception of the same thing, the reception is very similar to that of the product modulator based detection. That's just like we had it for DSB as well as for the SSB signal. So here what happens is simple, that we will feed the SSB signal here. The SSB signal comes in, there is a product modulator once again where there's a multiplication that is happening, and we have a carrier. Okay, same process, carrier, which will have a kind of a CT as it's mentioned. So SSB signal will have like ST. Already just now we had, so this ST, what we have generated here. So this is SF and this is ST. So this ST is fed over here. The carrier is over here, and then the output, whatever is we are getting, we will pass it through an LPF, because always the low pass filter will allow the message to come in. So the output V0 T will be nothing but some form of XT that will come in. All right. So if I just happens to do this once again, so let me just try to do that. So MT, remember that we have to calculate in the frequency domain, particularly for VSB, because it's easier for us to do. So ST multiplied by CT. So this is basically done by the product modulator. Now already if I convert this into frequency domain, so this will be MF equal to SF multiplied by CF. All right. Now SF, we have just now calculated everything. Okay, everything we have just calculated. So it should be VC by 2 X of F minus FC plus plus X of F plus FC. So this is basically SF. Now this is basically a carrier. Now this is represented as, again in the frequency domain, if I go to frequency domain, it will be represented as half of delta F plus FC plus half of delta F minus FC. For people who might not be familiar with this, just remember that this we had already done a long time back when we discussed the AM generation. If you go back to the previous day's recording or the document, you will find that this was again done in the case of carrier representation in AM generation as well. Because remember, we are doing it all in frequency domain. That's why we are using this as an equation. So we are looking at some form of this. So your SF and the carrier all together, final outcome would be looking something like MF equals VC by 2 X of F minus 2FC. I'm just writing the final expression. Okay, F plus FC plus sorry, not plus, multiplied by H of F plus FC. Okay, and here it should be an H of F minus FC as well. So this is in bracket, plus the other term should be VC by 4 X of F H of F minus FC plus H of F plus FC. So this is the overall expression that will come in. Okay, no need much here, but this is the overall expression. Now you can observe clearly that the first term that will be eliminated by the filtering action. Simply, this can be eliminated. Why? Because it doesn't contain any X. You can see the X lies somewhere here. So we need to extract the X. So in the first term, that is this one, if I box it, okay, this whole term is neglected completely because of the filtering action. So what we are left with is MF, if I consider, or V0 F in this case, suppose this will be equal to V0 by 4 or VC by 4, sorry, VC by 4 X of F H of F minus FC plus H of F plus FC. All right. Now, ideally, if you ask me that, sir, what is this portion, the right hand portion? So this portion you are looking at, okay, this is called as the filter gain. Okay? Filter gain. This is nothing but the ratio of the input to output ratio of the filter. So it's a constant. That's a constant part. Okay, and you can see this portion. If you leave out this, the only portion that we are left with is VC by 4 into XF. So this is again the same term that we were referring to. So this is a scaled version of the X of F. So that is whatever the transmitted signal were there, we have got that, but in a scaled version of the same. Okay, so this is about the VSB signal. Please remember that this VSB, why we are doing this actually, that this is a prominent solution, the application wise. If I go to the application, VSB is the only way, okay, that is usually used, the technique behind the general TV transmission. Okay, so this TV transmission that all of us are all familiar with all throughout the world, it might be different frequency, different specification for the allowment of USB to LSB, whatever the ratio of FV that we are going to consider for the transmission, that is separate. But the fundamental background process, okay, the principle of TV transmission all throughout the globe is done using the VSB transmission. Okay, so that is why it is so much popular and so much useful. And what happens, in fact, that if you just consider in that way, that if suppose the generic AM was used, okay, the full carrier transmission, we have observed that in this, suppose there's a the transmission was taking place around 4.2 megahertz and all. This is standard in US actually, this TV transmission scheme. So what happens is that the bandwidth is relatively less. We can reduce the bandwidth to certain extent while we are transmitting the channels. And another advantage for this is that since in VSB, in TV transmission, we have to transmit both the video as well as the audio simultaneously. So basically at a time there will be two transmission that will take place simultaneously. Otherwise video will come, audio won't be there, or audio will come, video won't be there. So naturally that is not a very pleasant viewing experience, right? So audio and video both has different carriers. So both of these carriers can be tuned correctly using VSB so that the TV transmission takes place smoothly. Okay, so you can read different articles on this. You can see the interesting part of VSB, but we don't need that. So that's why I'm not going much into that. But this is the application of it. All right, so this concludes our discussion. I'm sorry, this concludes our discussion on the AM modulator and the overall structuring of it. So what I thought today, that whatever the final day that we have to like we have classes next week also, but since we are finishing the second module, I want you to summarize. I want to summarize what we have observed over the period of time now. So this is last few slides and few numericals, if possible, I can solve with the time we have. That will be the end of the second module. Okay, so one of the thing is that we have found out what are the disadvantages of SSB because of the high filter action and all. But what are the advantages of SSB? Okay, so one of the biggest advantage that we have already calculated, in fact, that the occupied spectrum space is smaller. Okay, so that is one of the advantage, and also power can be saved significantly. That's why we have seen that the improvement is happening. All right, and disadvantage already we have mentioned. Coming to VSB, the one that we have discussed right now. So the main advantage of VSB being the reduction in bandwidth, okay, compared to DSB-SC, but it is almost as efficient as SSB. It's not that exactly it is efficient, like it is not exactly comparable. And as I said already, around 25% more bandwidth requirement is there for VSB. Okay. And due to allowing of transmitting part a lower sideband, the constraint on the filter have been relaxed. This is the most important factor that we have to consider for VSB, that the filter designing becomes easier. Okay, so they're practically easy to design filters. Okay, and it possesses a good phase characteristics, makes the transmission of low frequency component possible. So the amount of phase error that was introduced in the previous cases, those are significantly lowered. Okay, so this is the advantage. Now let us see a comparative study on the different power equations. Remember, we have discussed this already, but since it was quite a long time back, I thought of giving a consolidated results over here. So one of the equation what we derived was the total power transmitted. This is for the AM we are talking about. So in case of AM, it was the carrier power to that of the two sidebands which were present. So if you closely observe, here, hopefully this you are keeping a note of it. So this is my PC. Okay, this is my PUSB. And this may be my PLSB. So this were the total power that we are considering. All right, and in that aspect, we have also found out that what is the efficiency of the info, and that came around m² by 2 plus m square. This also we had derived in fact last during the class also. So if you got the value of m, you can directly substitute in these equations and you can get the power efficiency. Ideally, the power efficiency is nothing but the power of info to that of the PT. Now you can see this is a general way of doing it. Suppose the question is twisted a little bit and you get confused that sir, this is missing, that is missing, like that. Suppose you have, see, the efficiency is calculated based on info, the power that is required to transmit the information part to that of the PT. So ideally info is what? Info is nothing but USB plus LSB. So you can see that's why this part has come in and we have neglected the carrier. So definitely PT will be more than the P info. So in the other cases, the DSBSC, the SSBSC, we are trying to improve this efficiency by making sure that the carrier power is subsequently not present at all. All right, so this is one. So let us go back to AM once again, since we started off from here. The efficiency is limited to 33%. So because M equals to 1 is the maximum that we can get. So only 33% efficiency is what we are getting. All right, the carrier signal is present even if nothing is being transmitted, and the circuitry, the advantage is the circuitry is very simple because it's nothing but a signal, a basic sinusoid or a message signal, and which is getting added up with a carrier signal. Simple, that's it. Okay, and bandwidth is also 2FM. So that also we have discussed. Now coming to DSP, the same thing happens except that we are only allowing the USB and the LSB to operate, and the carrier is some completely subsized. So you can see the final outcome, the efficiency in this case. In fact, if you consider, this is given by almost 100% in the ideal case. It won't be happening, but in ideal case, because you can see P info is nothing but the accumulation of this one only. Because both USB and LSB, if you consider for DSBSC, that is where the information is. So P info is nothing but PT by PT, and that is around 100% efficiency can be obtained. That is the mostly of the option. So it's a higher power efficient system. Okay, and similarly that it has a bandwidth which is similar to 2FM, which is same as AM. So there is not much of an improvement in terms of bandwidth requirement. It requires relatively expensive circuitry in the receiver, because the detection process, if you remember, there also we had used the phase discriminator method or the sequential generation of using product modulator, and we have observed the problem that happens with the power, the phase error as well as the frequency error. So those things will happen. So we have to add as additional circuitry to eliminate those errors. And finally, we have to SSB, the one that we discussed already. So this is only either USB or LSB that we are transmitting. Same way, the efficiency can be 100%. Yeah, I think I got disconnected. Up to what point you have heard? Guys?
So you were just telling us about VSB.
DSBSU. Okay, till DSBSC, I was there, or I got disconnected before that.
No, sir, we could hear you.
All right. So, so I was nothing much. I just discussed the SSB after that. So in SSB, the same thing. The USB or the LSB is what we are transmitting, but it is the most expensive circuitry. That is the most problematic scenario. It is the most expensive circuitry, and that is only because of the filter. Very important, this one. Okay, and it has a extra sideband filter, new thing that came up. Okay, and the bandwidth was efficient, so it was FM, but the problem is the generation part. And this is again a comparison of the different modulation scheme. Already we have discussed this, but it's just for your own reference and later on so that you can understand. So you can see as far as the spectrum is concerned, DSB is something like this. Okay, where we are up the USB and the LSB is being transmitted together, and the carrier is null. Whereas in SSB we are either, you can see it's just become half. Okay, just closely observe this diagram. Okay, just this portion is missing. Okay, or this portion is missing. That means it's either ideally transmitting the USB of the signal in this case. If the other portion were there, then the LSB would have been transmitted. And you can see the VSB, what is happening, that it's the same thing, that this portion is fine, but the portion that you are looking at as a small little triangle over here, this is nothing but a portion of the LSB that actually has come in because of the VSB process. Okay, similarly, you can see these are the very important equations which I think I have already shared with you, and I will be sharing this also with you so that it's a consolidated thing. So you can see the first thing, the application part, I was telling you the VSB. So VSB is a TV video component. So this is what it is being used all throughout. Okay, as I said, like the AM transmission, if I go back to the previous one, the AM transmission, nowhere it actually happens because of the noise performance, which is very poor, as well as this is not a bandwidth efficiency, not a bandwidth efficient system, as well as it is not a power efficient system. All right, so that is how it is. SSB, again, as I said, it's a point-to-point communication, military purpose, different band. But again, the problem is the same because we have a problem with the filtering action. So that's why naturally it won't be used or that much. So that's why please remember that VSB happens to be the one of the important most modulation technique that actually comes into play. All right, so this is all about the comparison of different structure, different equations. Also, you can see here I mentioned some of the important equations for each and every segment of our discussion, and hopefully these all are mostly clear to you, because based on these equations only you can solve the different numericals which might be coming in for your Cat 1. All right, so with the time whatever we have, let me just quickly 1 minute. I'll just. Okay, let me just see one thing. I'll stop sharing for just a while. And let me just check, okay, that how many of you, can you please raise your hands regarding how many of you have gone about checking the assignment that I've given, the numerical assignments which I have mentioned. I told you to go ahead with the question, so I can see Sharad has done it. Okay. Okay, 5 odd. Vishalini is there. Gaurav, Navina, Sanchi, Srivastav. Okay, Gauri, Sneha, very good. Okay. So, okay, so I can see that as far as the viewing is concerned, 34 odd people have viewed. So all of you have seen it. Shovik, is it Shovik, right? Shovik, are you there? Shovik Mukherjee, are you there? Yeah, you haven't turned in. You raised your hand. You haven't turned in, I guess. Fatima, have you done it? Fatima?
I couldn't complete it, so I didn't turn in. I tried.
Oh, all right. Okay. So what I can see that from the hands itself, around 14 people have submitted, I guess, which I will confirm later. And as far as the people who have not turned in, or at least I would hope that you have gone through the numerical and at least have solved it. What I will do today, in fact, that I'm going to upload the answers and the solutions for those particular questions. Okay, so that you can drop your hands actually. Okay, you can lower your hand, no problem. So in those cases, so I'll upload the solution of the questions, so you can verify, self-verify, in fact, that whether your answers are correct or not. If not, you can let me know. But I have few specific problems apart from those which I thought of telling you, because those are pretty interesting problems, in fact. So whatever the time we have, at least quickly I can tell you the statements at least, or if we are not able to finish it on time. So let me go back to the sharing mode once again. Okay, so I'll just do it. Yeah, I'll just write it over here maybe. So you can make a note of these questions. They're also very important, I would say, like the equations and the process will be the same. Simple as that. There won't be much of a change in that aspect. It's just the terms somewhere, the representation of the questions will be a little different. So don't get confused. So read the questions and then apply your thoughts. So for example, this is a very simplistic question understanding wise. So suppose the question is an SSB signal. Okay, and SSB transmission. I'm just writing a little faster. Okay, short. SSB transmission contains the power 10 kilowatt. Okay, so I'll write in short. PSSB is 10 kilowatt. All right. Now the question is, this transmission is to be replaced. This transmission needs to be replaced by a standard AM modulated signal. All right. So SSB signal is to be replaced by a standard AM modulated signal. With the condition is with same power content. Okay, so the question is that with the same power content, a SSB signal is converted or to be replaced by a standard AM signal. Then find out, okay, the power content. Find out the power content of the carrier. Okay, and plus the next option is each sidebands. So each sidebands. So because it's a general standard AM modulation, so power content of the each sideband. Okay, when the percentage modulation M is given by 0.8. All right, so this is the question that we actually have. So can anyone please volunteer and tell me that how we need to proceed with this? Anyone? How we are going to solve it? Very simple. Guys, I'm waiting for an answer. SSB transmission power, total power is 10 kilowatt. The condition is that it needs to be replaced by a standard AM modulated signal. But the condition is also there that it should have the same power content. So your answer actually lies here. The same power content. This is what is important. So by that, what I mean is, you can see I was expecting a very prompt answer for this, that PT, total power, should be somewhere equal to this PSP, SSB. Is it not the case? PT was just now we had discussed the total power of an AM signal is total power is PT, which consists of carrier power plus USB power plus LSB power. So the total power of a standard AM signal is to be equal to that of the PASSB. So that is what the equation is. So simply we can substitute over here that PT, we can write it as PC plus PLSB plus PUSB. All right. And naturally, if I go on doing it, it will come around 1 plus M square by 2. So PT will be like this. Now PT is equal to this is equal to 10 kilowatt as given. So we can substitute over here as 10 kilowatt, that is we will convert into watt maybe. So like this 10,000. All right. Now if I look at all right, let it be. So this is how it is. So M, if you substitute 0.8 over here, so your PC 1 plus 0.8 whole square by 2. So like this. And finally, we are getting a result as PC is nothing but 7575.76 watt. Now, if you know PC, you can go on finding out what is USB, what is LSB, and that will be the two other answers that we are supposed to get. So it's a very simple question, but it's basically you have to understand that where to start. What I feel for all these questions, they are a little difficult in sometimes to understand that where we have to start doing it. Okay, another question maybe with the last few minutes, whatever we have, just to make you understand one concept here, one small little uh, term, and that is that suppose an AM broadcaster, the second question, AM broadcaster has a total power of 50 kilowatt. Okay, so suppose PT, so PT, I'm writing in short, it's 50 kilowatt. All right, so this is given. Suppose now when the carrier is modulated by a sinusoidal signal with the index M is 0.707. The question is not difficult here. Now the question is, first of all, question one is find the carrier power. So I guess now it won't be difficult because already we have solved a similar question right now. Comes to the transmission efficiency. Just now we had given the formula to you, but still eta is equal to m square by 2 plus m square. So this was the equation that we were referring to. Substituting m equal to here, we will get the efficiency. The third point is what I want you to focus more on. The third question is the peak amplitude. Please make a note if possible. Peak amplitude of the carrier. This is determine the peak amplitude of the carrier assuming the antenna to be represented by a 50 plus, please make a note of this, J0 ohm load. Now what exactly it is, and if suppose this type of question comes in, what you are going to do. So that is why this question is. The other two portion you can manage, and this one also you can manage if you know what exactly is this. So this 50 plus J0 that you are looking at over here, this is called as impedance actually. So okay, this is completely out of our course and everything, but impedance is nothing but you can say grossly that it is also a representation of like a resistor. Just like we will use a 5 ohm resistor, we will say in that way. So this is also a form of resistor, but here the representation is something like this: Z equal to R plus J. I think it should be around JX, maybe something like this. Okay, so this is impedance, R is the resistance, and X is called as the imaginary factor. This is usually very evident, and this impedance representation is very common when we use the AC and DC, like in circuits analysis where we have required the AC analysis also, there we usually use this. But for our case, we don't need to go for so many problematic scenario. What you have to understand is that the first term over here, okay, that 50 that you are looking at, this is nothing but the R, that is a resistor. Please keep in mind this. And if this is 0, this imaginary part is 0 in this case, right? J is 0. This is an ideal condition, or this is called as ideal resistor, ideal impedance for that matter. So at ideal impedance, our resistor value is equivalent to the impedance value. Okay, so impedance, and so because if X is equal to 0, Z becomes R, so your 50 becomes R. So now if you try this third one, we know, I think we can all do the question. So if suppose carrier power is given by EC square by 2 into R. So this was the equation already we have derived. All right, so EC is what we have to find out. So EC will be given by PC multiplied by 2R square root. Already you are calculating PC in the first case. This is your PC. So you have already found out that place. So you can get the value of around 2 kilovolt. You can just try out and find out the solution. All right, so these kind of different tracks, different questions, I would also collect a few more questions and I'll share it with you. This also, these questions that I just now had done. Also, this type of questions also, a few more, in fact, I'll collect and I'll add up in the course material whenever I'm uploading the documents. So don't worry. And that will be the end of the second module. So both first and the second module will be there in your syllabus as far as the syllabus is concerned. So I'll just do one thing. 1 minute. Give me just 1 minute. I'm taking more time, in fact, but yeah, if I just share you this one, I think it will be clearer to you where we stand for the time being. Yeah, so this was the syllabus that we had already discussed a few times back. So already the first portion, first module and the second module, till today, all are done. So coming Monday, Monday we don't have a class. Tuesday I think we have a class. No, Tuesday we don't have a class. We only have one class, is it? Do we have only one class? Guys?
Sir, Wednesday.
Only Wednesday we have a class, right?
Wednesday and 2 days.
Wednesday and today. Today is done anyway, so Wednesday is the one day. So what we are going to do is that on Wednesday, we are just going to start off maybe with the one of this segment. Okay, this is all are very simple. In fact, this relationship between FM and PM and all small little things we will start. That only portion will be added up with the portion that we have done in this. All right, so that will be the Cat 1 syllabus, but primarily your focus should be on this first two module and whatever we have discussed so far, at least for today. And whatever we are going to do on Wednesday, you can keep a tab that will be of only a very small segment that will be present from that portion. Okay, so sorry for keeping you waiting. I'll stop the recording and we'll come